Planarity and coloring. My screen is visible.
Yes, sir.
Okay, fine. Now here, in this topic, it is we will learn about that is the aims and objectives and the introduction and a planar graph and preliminaries and a dual graph. Euler's formula and vertex of the coloring, vertex coloring, intersecting results and applications and edge coloring. Summary, this kind of observations we will study in this topic. Where planarity and coloring is an important aspect we will study now. Now, aim and objectives of this topic is a aim going through this unit. Define the planar graph, faces of the planar graph, incident of the face, and F with the vertices and edges in the boundary of F, and a degree of the face in a planar graph and a dual graph. Next, to prove a result and regarding the design embedded of the graph in a plane, find an embedding in the which a vertices lies in the exterior faces, and finding of the sum of the degrees of all the faces establish Euler's formula and discusses the consequences. And the coloring point of view discussions will come to the here. Define the coloring, K colorable and chromatic number, K chromatic and K critical, K edge colorable, and K edge chromatic of a graph. These definitions we will study in the define of the coloring. In the necessary condition for the graph to the K critical, and observe that is the nature of the vertices of the K chromatic graphs, and finding the upper bound of bound for the chromatic numbers and the lower bound of for the edge chromatic numbers. These concepts we will study here. In this introduction part, we will study that is as we have seen in the unit 10, the previous classes, it is a drawing of the graphs. Previous class also, before last classes also we discussed the graphs information. The graph is whether it is possible to draw that is a graph in which the way to the number of edges, crossing of that each edge, two edges meet at a point other than the vertices of the graph. If the such a graphing is possible, we call that is a graph as a planar graph or not. This is a concept playing that is important role. When we say that is a two graphs of the planar graphs means it is the only intersecting point discussions it will come out. So here intersection part is, of the edges are not there. It is called as a planar graph. The concept plays the important role for the design of the electrical circuits. The two circuits should not be intersect. If you intersect, it will become that is a short circuit. Such problems of the design of the motherboards, design of the all the things, televisions, all the mobiles. It is a circuit should not be intersect. There is any two edges. Otherwise, it will come into the short circuit. Such kind of the things I want to be removed means it will be come into the planar kind of the problems. In this the planar kind of the problems, the graph is a planar. When we can design the circuit on the single board with the no cross connections with the problems that are related to the coloring the maps, coloring the maps. Coloring the maps, here we can model a circuit with the graph by representing the components of a circuit by vertices and connection between that is them the edges. If this graph is a planar, then we can design a circuit on the single board with the no cross connections. It's the problems related to the colors, coloring the maps of the relations, regions. 2-3 regions will be there that which is the identification of the region that easily we can identify by using this coloring. Two regions with the common boundary represents the different colors. These can be easily solved by considering that is a dual graph of the corresponding graph. Using this, we can be determined that is a least number of the colors required. The famous conjecture, every planar graph is a four colorable of 1850 is recently is settled in the affirmative. In representing the graph by the plane means of the diagram into the two-dimensional space, only the graphical representation. So we can see in the coloring of the graph. If it is coming to the three dimensions, it is somewhat it is we can have to be identify some constraints and conditions such a way we can be identified. Next, coming to the it is a plane without a graph is set with the planar or embedded in a plane. If and only if it can be drawn in a plane without crossovers, it is the edges intersect only at the ends. Such an embedded is called as a planar embedding of the graph. Otherwise, the graph is called as a non-planar. It means that it's a planar means it is a there is no any cross cut. That kind of observations is comes to the it is a planar graph. Next, conveniences when we take the planar graph with the associated the diagrams as the planar embedded, we refer it as a plane graph. Example, if we take that is three living the places in each of which is connected by the cables to organize the origins of three service centers with the supply the gas, television, and telephone connections. And now the problem is whether it is possible to connect each unity outlet. It is each of the three living places. Such no two cables should be the intersect. Such way we want to be arranged. Next, association of the graph problem. If we take that, it is there is the vertices is represented the six locations. Each cable by the edge joining of the two vertices is represent the location and service centers. So this is a three graph, nothing but it is a K33 we can represent. The three is a planar or not. That is a we want to identify which is a non-planar or not. We can show that observations. Here, this graph is must be the planar. If I want to draw the planar embedded of the graph you mentioned, it is the given graph is a planar or not. It is clearly it is not a planar because of it is intersecting that is a V2 to V5 on V1 to V4. And one edge is a V5 to V3 also it is intersecting. So these kind of intersectings are the very difficult, so that we should not be embedded in the graph, so that way will be removed. Then I can get that is a new kind of then I can get that is a new kind of graph. Here you can see that is a graph is a planar or not. 13.3.11.
Sir, that means that is not planar graph, sir.
Yes, it is not the planar graph. But if I want to make it into the, this is a way I can make the into the planar graph. So what I did, that is the extendable, I have drawn that. Because of edges are not connected to each other, it is not touches to each other. This is the formation. This is clearly what it is. A graph is appearing 13.3.3. This is a planar graph. So whenever you will give that is a non-planar graph, that will be we want to be convert. We can be converted into the planar graph. This is a overall idea about it. How we can be converted into the planar graphs. Now, this is where they have shown that it is a, this is clearly we can conclude that it is the edges are touching for each other, so that it is not the planar. And that in the example shown that it is a draw that is a planar embedded of the graph or not. It is clearly, if we change that diagonals, where it is intersected, that will be changed into the some another way. That and I'm not wasting that is the edges. I'm connecting with the edges to the each other, but which is a closing, combining that, so that it is clearly appears that is that the graph is called as a planar embedded of the graph. Planar embedded of the graph. Next, it is a graph G can be the embedded in the plane, if and only if it can be the embedded on the sphere also. What is a sphere and plane? Plane means it is in x, y, z dimensions. What we have taken the 1 point observation that is comes to the plane. That points connections it will be appear in the plane that comes to the graph. Now it is a sphere means it is a, if I take that is a total 3 dimensions and a third dimension we cannot be visible in the graph. It means that it is a, for example, one rectangular box is there or a house is there in front of you. The back side of house, what it is happening, we cannot see. So if we see that it is not the sphere. If we cannot see means it is that is a sphere because of the third opposite direction. So we cannot see that what we have. That is the overall idea about it. It is whether we can see or we cannot be seen. The graph G can be the embedded in the plane if and only if it can be the embedded on the sphere. This is the overall idea about it. Now coming to the proof of the, suppose G is the embedded, says that is a G dash on the sphere. Choose a point P on the sphere and the knot in the G dash. So I'm taking that is a G is the embedded and it's a G dash is on the sphere embedded or not on the plane. So it is a choosing that is the only point on the sphere and it is not in a G dash. Because of G dash is I consider the plane region and not the sphere region. G is the sphere region I consider. So considering the image of the G dash is under the graphic projections from the P, so that we can be follow that is embedded of the G in the plane only, that not in a sphere. So it is a converses, it is a 2 marks, 4 marks questions or 5 marks questions. It will be the, here we will ask in a 5 marks question is this kind of observation. Now it is a G is in a plane of that. Next preliminaries, if I discuss that, it is a G is a planar graph. The planar embedding of the G is a partitioning partitions the plane into the number of connected regions. The closure of these regions is with respect to the usual metric on the plane are called as the faces of the G, like that is we can be called. Now G is a planar graph that f of G and pi of G denote the set of the faces of the number of the faces of the G representations. Next observations, if I take that, it is a bounded or unbounded region. And one more is interior faces or out exterior faces. If I take that as a plane graph, it is exactly one unbounded region. Bounded region is a graph is a bounded means it's connected. Bounded, unbounded means it is not the connected. So this is called as exterior faces or interior faces. Exterior faces of the graph. Unbounded region, and it is having that is some exterior outside as having that is in the region of the points. Now, if I take all the other others are called interior faces because of interior regions of that. Now, considering this observation of this graph, here of 13.4 to 4.4, the 5 interior faces we have, that is what is that F1? Here it is bounded by the region only. F2 it is also bounded by the region because of in the upper lower half circle where it is there. This is a V2, V3 and E5 edge. That is a space region. Next, coming to the another will come to the, it is a F3 also bounded, F4 also bounded, F5 also bounded. These all are the bounded regions, so that it interior faces we call. It is a point is outside, it will be there. It is exterior faces, so that we can call it as the F6 is the exterior point. Now coming to the G, is a planar graph. 3 marks are the important term, 5 marks are the important term. G is the planar graph and mu is the vertex of the G. Then it is possible to take an embedded of the G such that is a U lies in the interior faces of the embedded. Previously, clearly it is a bounded, means it is called as interior, and unbounded is exterior. So while taking this is a planar graph, edges are not touchable, and U is a vertex of the G. Fine. Then it is possible to take the embedded of the G. The embedded means it's connected of the G, such that is a U is a lies. U is lies. U is lies. Exterior faces of the embedded. It is the interior is not there. If we prove that, it is comes to the exterior. If I take that is a stereographic projections, if I take that as stereographic projections, if I take the stereographic projections, my screen is visible.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Yes, fine. Thank you. This is a 13.4.5 is important for the 5 marks question. G is a planar graph and U is a vertex of the G. Then it is possible to take an embedded of the G such that U lies in interior faces of the embedded. Just now I discussed interior means it is a inside will have, and exterior means it is outside will have. Interior, it is a graph, it is clearly connected with the bounded. So, to point of view, I've taken the G is a planar graph. By the known result of the previous one, there exists that is the embedded of the G is in his on a sphere. It is denoted that is a G dash considered as a face and a face that contains U because of it is a bounded. Let P be the interior point in the face, and all the embeddeds of G dash, it products, if I take and G dash into G dash into G dash, all the U combined product, if I take pi of G dash be the image of the G dash under the stereographic projection of the P. It clearly follows that pi of G dash is a planar embedded of the G, such that U is the point is exterior faces of the embedded. The simple way, the planar graph, so that directly we can conclude that it is having that is a dot connected with the any repeated edges, and but it is outside faces will be there. It is exterior embedded. It is it possible or not, that we can be checked by using the stereographic projection from the G, from the P. Any point is interior, then it is a stereographic projection is outside only, so that it is a G dash. That kind of all graphs G dashes, sphere graph outside graphs G dashes in the planar embedded of the G, such that U is the point is in the exterior faces of the embedded. Now the boundary of the faces of the plane graph is denoted by the B of F. Now, in a plane graph, face is said to be incident with the vertices and edges in the boundary. Faces is said to be incident with the vertices and edges in its boundary. It is the vertices and edges in its boundary region if we have, that is a planar graph, so that it is we called as an incident. That's all. So from the planar graph, if I take that is a 13.4.4, this is a graph. In this graph, the plane graph is given by the example from the F1 is clearly inside the vertex. So V1, V2, V3, V4 are the vertices and edges are E3, E4, E5 and E6. E12 are the vertices and edges. So it is clearly inside F1. F2 also inside. F3 also inside. F4 also inside. Inside of the vertices are the V6, V7, V8 and edges are the E8, E8 and E11. Same way we can reflect that which is interior and which is the exterior. Now I will take that as a vertex V5. V5 also incident. V6 is a incident with the vertices of the edges E1, E2, E3, E4, E6, E7, E8, E9, and 1 and 12 also. So where is the F6 you see here? F6 is clearly outside, but it is a bonded with the here V1, V2, V3, V8. It means that is the total outcome it is. And V4, V5, and even E2 like that. It means that is outside region is also be considered also incident because of it is connected with the vertices and edges. That is also external region, maybe, but it is a incident because of it is connected one of the plane region on. And E6 and E2 and E7, if I cut the edges, they are incident only with the F6. That is only the specific observation. Next, coming to the planar graph G, it is edges are not repeated. G, I am taking. Degrees, if I observe, there is a degree of the F of the face F in G is the number of edges incident with it, and it cut the edges in the beginning counted twice. So it is a planar graph will be there. The degrees of the face F in the G is the number of edges incident with it, and it cut the edges in the beginning of the counted twice. Double it will be counted. Now graph is G is collected, boundaries of the edges and degrees of the faces we want to be identified. So how I am identifying? This is a graph only. Here first is a V1, V2, V3 is a triangle, and V5, V6, V7, V8 is a rectangle, and another loop will be connected from the V6 side of V8. At bounded regions and unbounded regions will be there. All are the incidents. Now he's asking that is to calculate the boundaries and the degree of the faces. So all F1, F2, F3, so are the boundaries and incidents and the degrees of the faces. So I want to identify. So 13.4.3. See here, boundaries of B of F of 1 equal to what are that? F1 boundaries, it is a triangles. So that I mentioned. Next with the edges connections. And BF2 boundaries denoted by the BF3 boundary of the 3. BF4 boundary of the 4. BF5 boundary of the 5. Degrees of F1 means how many edges we have. That is the counts we should be right. Similarly, it is a vertex also. Sorry, it is a degree of the F3 means it's the edges. How many edges it will be corrected? That is to the F3. And the same way, it is a degrees are connected with the F4. That is how many number of edges we have. That is only 3. Degree of the 5 it is connected with the 8. So the total how many we have? 2 types of limit. So that twice the number of edges. Twice the number of edges. That is a very clear observation. We got it.
Sir, in this figure, what is 1, 6 वो क्या है sir?
DG of f of 1 is equal to 1 बोलते क्या है सर ये?
एक मिनट फिगर ले लेंगे
उसका आंसर्स में 13 4 13 का
ठीक है F1 बोले ना F1 बोले तो इधर एडजस्ट
नहीं वो नहीं सर उसके ऊपर का 13 4 13 का आंसर्स है ना सर आंसर्स में
yes 13.4.13 I am discussing
हाँ जी जी जी
हाँ क्या बोले बोलो
ये B of f of 1 is equals to V4 E3 V4 है ना तो उसके इक्वल DG
F1 surroundings what we have
yes sir वो I understand but ये 1 क्या है ये DG f of 1 is equal to 1 है ना
इधर कनेक्शन से एडजस्ट कितना है
okay thanks
E4 is connected with the V3 to V4 वही बोले तो E4 में एज एक ही एज है ना ये एक ही एज में डिग्री होता
E4 ओके
डिग्री आते मालूम है ना
ओके सर
ठीक है राइट उन एग्जाम में वो लिखने तो बस 5 मार्क देते हो ना एग्जाम
ओके
और ड्यूअल ग्राफ बोले तो हियर two graphs we want to be dual means what is a two one graph name is a G another graph name is a G star G is a plane graph and G star is also graph obtained from the falling from in G that is also I will get from the G on so each face in F in G there is a vertex of F star of G star and corresponding to each edge E belongs to G whereas the E star of G star and vice versa. Two vertices of the F star and G star are joined by the edges E star and G star. If and only if it's correspond to the faces of F comma G that are separated by the edges E in G. The graph G star is called as a dual of the G. So graph G star is we will say that is a dual of the G. If it satisfies the conditions of F star and G star is joined with the edges, E star in G star. If I take that it's corresponding that F and G must be the edges of the separated by the edges in E in G. That is clearly fulfilled, then we can say that dual of the G, dual of the graph G. It is generated by the G star. First graph बोले तो G और दूसरा स्टार में है ना that is called as a dual of the graph. The graph one G graph that we can make it into the dual of the graph G star. That is only the observation we can see in a dual of the graph and an example of the graph and dual of the graph. You will ask in the examination, define the planar graph and its dual of the graph. At the time you draw these two and I explain about that, it is a any 2 points, it is a graph G. From that we can be established that is a G star. G star is clearly satisfied that any two connectivities of the rebounded regions F1 and F2 that will be in a G, it will be converted to the F star, F1 star into F2 star like that. So this is an explanation if you give, it is called as a dual graph is enough. Now coming to the remarks of this dual graph is that is also planar graph only, not in a separated graph. And a dual graph G star in the plane, if I take the vertex of the F star in the graph corresponding face F of the plane G, then we can draw each edge E star of the G in such a way that is the cross corresponding of the edges E belongs to G exactly once. So already it is a planar graph means its edge must be the one only. So it is a cross cut is there happen, it is no other edges in G. So that it is not the planar. So here example, if I take that it is a graph G, how it will be, we can make it into the dual graphs means it is a, this is a original graph and another connectivities we can see that. This is G star is called as a
dual graph.
Dual graph, that's all. Sometimes we will give the graph G and a dual graphs you should be connected. G is a plane graph and G star is a dual. Then the usual notations of the vertices of the G star and the vertices of the G star is clearly vertices of the graph G only. So vertices of the G star is clearly vertices of the G, and edges of the G star is also edges of the G only. And the degree of the G star is of F star is equal to the degree of dual graph of F also. So dual graph of the F star is also equal to the dual graph of the F only. For all F belongs to F comma G. That is only the observations we can see in the graph G and G star dual. These are the notations from the vertices as well as the edges. Now this is important. It is a any planar graph. It is a notation is comes to the degrees is a two kind of edges it will be there. It is a simple way. It is a G is a planar graph, so that it is a G star is a dual. I am taking summation of all the degrees of the F. It is summation is a I am taking in the graph G. If it will be the converted into the dual graph, it is a summation of the degree of F star. F star is clearly belongs to the vertices of the G, so that it is a all edges means 2 times of edges of the G star, so that 2 times of the edges of G. That's all. Next to Euler's formula, if we come, it is a relation between the number of the vertices, edges, and faces in the connections. That is a plane and finite graph is obtained in the by the Euler. In the Euler formula, what he mentioned, that is a clearly when we have the vertices, edges, and faces of the connections, then the finite graph is clearly observes. The usual notation is a V minus what is this number of vertices minus number of edges plus that is a pi is equal to the 2. That pi is clearly we can get that is some empty set. That's all. Now, proof point of view, it is important for the long question. If G is a connected plane, finite graph I take it so that it is a finite graph. If the pi is equal to faces, if I take the pi is the faces, if the first face, if I take, if phi equal to 1, it is the first face, then the number there are the no cycle in the G because of only one. How many vertices we have? Only one, so that there is no any other connections, so that there is no cycle formation. If it is a cuts edges, if I take, then it is a G is a tree. By the following that is a epsilon equal to what is that? V minus 1. So that implies V minus a epsilon, V minus epsilon means edges only. V minus edge, vertices minus edges is clearly 1. So that V minus the edges is a plus pi equal to 1 plus 1 equal to 2. Let it be that integer I take it. It is greater than or equal to 2. It assumes that is the validity of result for all the such G's if the number of the faces are the less than n. Now G is connected because of all the faces, vertices, edges, so that it is a plane is a finite graph with its end is greater than or equal to 2 faces. It clearly follows that is a G is at least one edge. That is not a cut edge. So now I will take that is let E be the edge of the G, that is not the cut edge. Now E is lies on the cycle. Hence follow that it is a G minus E is a connected plane, finite graph. With n minus 1 is it is less than n faces. By induction hypothesis, G minus E edges is a connected plane, so that it is a n minus 1 is a with a graph of connectivities we have, so that it is less than n faces. So by the hypothesis we can write that is a vertices of the G minus E minus edges of the G minus E plus pi of G minus E is equal to the 2 by the principle of connectivity. Therefore, vertices of the G minus E equal to V of G and edges of the G minus E equal to edges of G minus 1. Pi of G minus E equal to pi of G minus 1 all together. Vertices of the G minus edges of the G plus here proof point of view we will take that is the vertices of the G minus E is clearly we can write a vertices of the G. That is I am substituting in the one. And edges of the G minus E equal to vertices of the edges of the G minus 1. So that pi of G minus 1 altogether it comes to the 2 only. So that V minus epsilon plus pi equal to 2. Since if and only if the one graph under the consideration, once it is incidence, induction is a proved. The resultant is 1:2. So connectivity it comes to the more than 2, then it will be clearly satisfied the condition. If I take the corollary of the two planar embedded of the connectivities, if I observe, then pi of the graph 1 is equal to the pi of graph 2. That both will be the same. That is one is a corollary means it is from the FO statement we can get here. Next, another corollary is the most important for the 5 marks. 13.6.4. So, if the G is a simple and finite planar graph with the V is greater than or equal to 3, then epsilon is less than or equal to 3V minus 6. So, proof point of view, I am letting that it is a G is a finite and simple planar graph with the V is greater than or equal to 3. Without loss of generality, we can suppose that G is connected. For the otherwise, we consider the each component of G since the G is simple. It is connected for that other, we consider the each component of in this proof point of view. Here G is a simple, he gave that it is a planar and it is a finite graph so that vertices are more than 3. At the time its edges is clearly less than or equal to 3V minus 6, it is a usual notations. So that G is a finite, I am taking the simple planar graph and V is greater than or equal to 3. So without loss of generality, we can take that as a G is connected. G is connected means G is a simple, so that it is the degree of the F is greater than or equal to 3 because the vertices are greater than or equal to degree of F also greater than or equal to 3. Altogether, it is F belongs to capital F. In the usual notations, it is a summation. F belongs to capital F and degree of F is greater than or equal to 3 into pi of G. By the known result, it will be that it is a 2 epsilon G is greater than or equal to 3 into pi of G. So that Euler's formula, we can take that it is a V of G minus epsilon G plus 2 by 3 times of epsilon G is greater than or equal to 2. Therefore, epsilon G is less than or equal to 3 into V of G minus 6. So that it is a epsilon is less than or equal to 3V minus 6. Hence it is proved. Now, corollary also, I can take for that it is if G is a finite and simple planar graph, then it is the usual notation. The minimum degree of the delta of the G is less than or equal to 5. Under the given hypothesis, the result is trivial when the number of the vertices of V of the G is less than or equal to 6. In this 13.6.5 corollary, if I observe, one second. No, చెప్పండి. అయిపోయిందా ఎగ్జామ్ సబ్మిట్ చేసినావా? టెస్ట్ 1 కంప్లీటెడ్ అని పడిందా? టెస్ట్ కంప్లీటెడ్ అని పడిందా? సబ్మిట్ చేయలేదా? టెస్ట్ కంప్లీటెడ్ అంటే అయిపోయినట్లే. అన్ని ఆన్సర్స్ సబ్మిట్ బటన్ వస్తుంది. ఒక్కసారి కింది వరకు లాస్ట్ వరకు స్క్రోలింగ్ చేయి. టెస్ట్ కంప్లీట్ అని అన్ని ఆన్సర్ చేసినావా ఏంది? అంటే టైం 1 అవర్ అయిందా? ఇంకా అవ్వలేదుగా, 2 minutes ఉంది. ఒక్కసారి పైన సబ్మిట్ బటన్ వస్తుంది, ఒకసారి చూడు పైన నుండి కిందికి. టెస్ట్ కంప్లీటెడ్ అని వచ్చిందా? టెస్ట్ కంప్లీటెడ్ అయితే అయిపోయినట్లే. ఒక్క నిమిషం ఉండి నేను అనుకుంటాను. హలో మేడం, ఇది టెస్ట్ కంప్లీటెడ్ అని వచ్చింది, అంతేనంటనా మేడం? ఎగ్జామ్ రాశాడు, టెస్ట్ కంప్లీటెడ్, సబ్మిట్ బటన్ రావట్లేదన్నా, టెస్ట్ కంప్లీటెడ్ వస్తుంది, అంతేనా ఆపేయాలని అడుగుతున్నాడు. ఓకే మేడం, ఒక్కసారి మార్క్స్ ఎన్ని వచ్చాయి ఒకసారి పెట్టరా? చిన్న టెస్ట్ కంప్లీటెడ్ వస్తే సరిపోతుంది. ఓ 2 నిమిషాలు ఉండు, ఒకవేళ సబ్మిట్ బటన్ వస్తే నొక్కేస్తే, లేకుంటే వదిలేస్తాయి. ఓకేనా? ఇప్పుడు ఆల్రెడీ టెస్ట్ కంప్లీటెడ్ అని వచ్చిందా అంటే టైం అయిపోయిందేమో, అది 2 minutes ముందే, 2 minutes ముందే అయిపోయి ఉంటుంది. ఎన్ని క్వశ్చన్స్ చేసినాం? ఎన్ని క్వశ్చన్స్ ఇచ్చారు? 50లో ఎన్ని క్వశ్చన్ చేసింటావు? 50లో 30 చేసింటావు అంటే కరెక్ట్ గా ఎగ్జాక్ట్ ఆన్సర్లు. ఓకే నాన్న, సర్లే, సరే చూద్దాం. రైట్, ఏమేమి ఇచ్చారు? మ్యాథ్స్, ఫిజిక్స్, ఇంకా ఓకే, ఇంకా ఓకే ఓకే, ఆ 3 పర్ఫెక్ట్ చేసావుగా. సరే 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 నాన్న, ఓ 2 minutes చూడు, వస్తే సరే, లేకపోతే అది వదిలేసే. ఓకే ఓకే చిన్న, రైట్. నౌ ఒక్క నిమిషము. Proof. If G is a finite and concept clear cheyalada. Okay. G is a finite and simple planar graph. These all are the corollaries we can get from the above theorem only. What is the theorem? V plus E minus F pi less greater than or equal to 2. That is called as Euler's formula. From the beginning, that is the Euler formula. We are getting these all. That is only the important things. Okay. అమ్మా, ఎన్ని క్వశ్చన్స్ అయిపోయినాయి చిన్న?
సార్ ఒక క్వశ్చన్ మాత్రమే.
ఓకే, అంటే 11:30 వరకు 1:30 వరకు కంప్లీట్ అవుతుందిగా. ఓకే ఓకే, 1:30 వరకు ట్రై చేయి. ఓకేనా? తర్వాత అవన్నీ PDF చేసేస్తే నాకు పంపించాలి. ఓకే. Now here, if G is a finite and simple planar graph, then it is usual notation the minimal degree of delta of the G is less than or equal to 5. Under the given hypothesis, the result is a trivial when the number of the vertices V of G is less than or equal to 6. Assume that V is greater than or equal to 7, greater than or equal to 3 by known result. The following follows that it is a epsilon G is less than or equal to V of 3 into V of G minus 6. By Euler's theorem on the degree sequences, we get that it is a delta of V of G is less than or equal to summation D of V equal to 2 times of epsilon G less than or equal to 6 into V of G minus 12. By 1, it is less than 6 into V of G. So delta is less than 6. So delta is less than or equal to 5. This is the complete the proof. Next, K5 is a planar. K5 means it is how many we have? 5 to 10. 10 equal to epsilon into K5. So that it is less than or equal to 3 times of B into K5 minus 6. So that 3 into 5 minus 3, 5 is a 15. 15 minus 6 equal to how much? 9. 9 is the context. So that it is clearly non-planar. I have taken the V5 is a planar, so that I proved that it is a 9. I got it, so that it is not a planar. It's a non-planar. I mentioned. K3, 3 is the another corollary. Is it the planar or non-planar? He gave that is a non-planar. He's asking to prove this one, so that it is what I want to do. It is a contradiction. I can take that. It is a 3 bipartitions we have. In these 3 bipartitions means it is a upper 3 and lower 3, and these all are will be connected. upper 3 and lower 3, these all will be the connected. Let G be the planar and embedding of K of 3 comma 3, since K 3 comma 3 is a bipartite, it has no cycle of the length 3 or 5. So if it has that cycle of length 4 and 6, this every cycle is of length greater than or equal to 4, then the degree of each face of the G is greater than or equal to 4. So by known result is a 4 pi is less than or equal to summation. F belongs to capital F, degree of D of F is equal to the 2 epsilon. So 2 times of 9 equal to how much? 18. So pi is less than or equal to 4. By the Euler formula, 2 equal to B minus epsilon plus pi is less than or equal to 6 minus 9 plus 4 equal to 1. It is a contradiction. Observations, we have seen that K 3 comma 3 is a non-planar. We observe that the minimum number of the edges is a non-planar. Graph is 9. Show that is a simple graph G with the 6 vertices and 13 edges are non-planar. That these are the questions solutions we have in the bottom that we can be referred. This is a total is comes to the planar thinking. Next, what is this coloring? Now I am discussing. What is this coloring I am discussing now? K be the positive integers and K coloring of the graph G is the assignment of the K coloring. K colorings says 1 to so on K to the vertices of the G. A K coloring to the graph G is said to be a proper if and only if the no two distinct adjacent vertices of the G receive the same colors. Therefore, the proper K vertex coloring of the loopless is the graph G is a partition V1, V2, so on Vk of the vertex set V of G, such that each element of the Vj is receive the same color. Sir, what is a coloring means? It's a K coloring. It is a coloring means it is what is that? It is a one bounded region. It is assignments of the group of the elements. Vertices are the connected. That group of the elements is of only one type that is comes to the coloring of that color of the vertices of the color. So that it is a K coloring means it is a K groups we are taking that. It's properly that two distinct adjacent side vertices of the G is receive the same coloring. That is the only idea of that. So that proper K vertex coloring of the loopless graph G is a partition to the V1 to Vk of the vertex set V of G, such that each element of the Vj is a reverse the same color. So J is equal to so on K. This is a equivalent to the saying that no two elements of the V3 Vj are adjacent in G. So it is all are the independent of the G. Therefore, it is a K vertices coloring of the loops of the G is partition to the V1, V2, so on Vk. Another definition is comes to the graph G is said to be the K vertex coloring, colorable, if and only if it have a proper K vertex coloring. K vertex are the colorings, then it is comes to the proper K vertex colorable, we can call. Next observations is a simple graph. If I take K vertices, then it is a K colorable, separated. Simple graph is a one colorable. If I take, it is a empty, no edge. The simple graph G is simple graph is a two colorable if and only if it is a bipartition. K vertices means K colorable. So here, how many simple graphs is based on that we can decide it is a number of colorables. That's all. That is the observation. So we can check here from that K colorable if and only if it is a simple graph K is a colorable. That's all. Yeah, 3-dimension chromic. Chromic means it is clearly here show that the following the graph is a 3 chromic. 3 chromic means once you see how many vertices? 6 vertices. Sorry, 7 vertices. Here edges are all are connected. Now 13.7.11 I am checking. This one. 13.7.11. Here, graph is a non-empty, so that it is a chromatic number is not equal to 1. The graph is contains K3. It is a triangle, an odd cycle. So it is a not by partition. Hence, it is a chromatic number is a not 2. Not 2 means it is a 3, 3, 3 will be the partition of the vertex of the graph. We have to be arranged. Each an independent set, so that it is assigned, say that it is a red, green, yellow to the subsets. Hence, a minimum of the 3 colors are required to have the proper color. Hence, it is a 3 chromatic. Here, how many bunches you are subsets you are dividing, that is called as a chromatic. Red, green, yellow, or the 3 subsets. If I take it is a 3 chromatic. I mean the 3 colors. The set of elements, which is a group of the elements having the same color, that number of the groups are called as the chromatics. Now, here, this is a following the graph. In that graph, how many bunches I can divide? How many groups I can do it? That is a left part and right part like that. So if I make that is a all the 3 vertices is the one group and another 3 are the one group. What about that is it is a single one will be the balance. That is also one color. So the 3 chromatic we can be decide. That is only the answer. 13.7.12 it is defines to the a simple graph G is set to critical. If and only if it is a proper subsets of H of G is a psi of H is less than psi of G. It is called as a critical graph to play the important role in the coloring of the graphs. It is a condition of subgraph. If I take subgraph is H. H is a subgraph of the main graph G. In this chromosomes, and it is groups. If I check, it is both the groups are the. It is always it is less than, so that it is called as a critical. Graph is critical means it is subgraphs are the subsets are the possible. That if we say that it is called as a simple graph G said to be a critical if and only if it is a subgraph, proper subgraphs. Next is critical. This is another definition. If I take that, it is a graph G said to be a K is a critical if and only case. K chromatic or criticals are the exist. K chromatic means K subgroups are the exist. Then it is called as a K critical. Here 4 critical graphs should be due to the Croges. So that it is, if I observe that, it is the partitions of the vertex set. Partition of the vertex set. Partition of the vertex set is a V1, V2, V3, so on V8 is a 1 chromatic. Simple way, it is a 4 chromatic means it is a 4 groups, so we should be divided. That's it. That is only the idea. So V2, V4, V11 and V3, V5, V8, V10 and V6, V7, V9 is also one group. And V1, V10 also one group. So that it is comes to the 4 criticals. That's all. Next, interesting results and applications on the critical and minimal degrees. So that it is if the G is a K critical, this is important number for the 5 marks question. If G is a K critical, then the minimum degree of the G is a delta is a greater than or equal to K minus 1. The proving of this is a contradiction. So let G be the K critical graph. And delta less than K minus 1. Let V be the vertex of the degree G, degree delta in G. Since the G is a K critical, if and only if the G minus V is a K minus 1 colorable. Here all vertices of the partitions of the G to V is corresponding to the coloring. V is adjacent to the delta vertices. It follows that V is not adjacent to the each element of the Vj for some J belongs 1 to so on K minus 1. V1, V2 to V3 so on belong union V of Vk. So gives us the K minus 1 coloring of the G. It is the contradiction that it is the G is a K critical. Delta is greater than or equal to K minus 1. And one more, it is every K chromosome chromatic graph has at least K vertices of the degree at least K minus 1. So let G be the K chromatic graph and H be the K critical subgraph of G. By the known result, it is each vertex of the H has subgraphs only. So that it is greater than or equal to k minus 1. Since that H is a k criticals. Equal to will be there, so that it may be the equal. It has at least k vertices. H is a subgraph of the G. It follows that G has at least k vertices of the degree, at least k minus 1. So that it is a proof that result. Corollary also the here x of G equal to k. If I take a k is greater than delta plus 1 from the above theorem, it is k is greater than or equal to delta plus 2. From this, it is a G has at least k vertices of the degree, so that it is a delta k vertices of the degree always greater than or equal to delta plus 2 minus 1. So that it is delta plus 1 only. Delta plus 1 means it is k greater than delta plus 1. So it's considered that maximum degree of the G is a delta only. So that it is our required result is a 2. Next, timetable scheduling. It is a fixed number of the subjects to the colored completed the specific courses. It means that it is a, for example, it is a chessboard will be there. Where are the timings are the not filled, that we should be filled with the same color subject wise. If, for example, I am taking the maths or some statistics or something else, it is the other subjects, English, physics. So that what is that all will be the subject wise, I will make the colorings. That coloring is clearly mentioned. That is a timetable scheduling. That's all. Example, it is a 7 courses we have. I am taking 7 students are having the 4 courses. Offering the 4 courses. So that is observed. That is the students is a common to everyone. The scheduling is a time is a, it will go for that this kind of the graph. And this is the explanation. What are that? It is a 4 groups. It is a red color is a 1 group, yellow group, and green and blue color. These are those who are the groups will be the make it. Next, edge coloring is comes to the. Let k be the positive integer and k edges is the coloring of the loopless. Loopless means it is a loop should not take. But it is a non-empty graph G is the assignment of the k colors. So that it is a what is the importance of the loop? It is not required for the loop. Its edges are available or not. Based on the edges, it is a coloring will be end. So that it is a loop will be there at the time. It will be considered for the separate coloring graph, so that it is also one separate set. That's it. Separate subset. That's it. So k edges is a coloring to the graph G is said to be the proper if and only if it is no 2 edges and the edges are the received that is the same color. These all are the observations. Definition is a graph G is said to be a k edges colorable if and only if G has a proper k edge coloring will be how, so that it is a k edge coloring will be the proper k edge coloring will be there. It is called as a k edge colorable. The edge, another is the definition. G is a loopless is a non-empty graph will be there. The edge chromatic is the x dash of G. It is a subset of the G, so that it is clearly minimum which G is a k edge colorable. That's all. A graph G is said to be k edge chromatic if and only if it is a psi of T, that is a subgraph of the G is equal to k. That's all. These all are the examples. And what we discussed the concept of this one means it is clearly introduction and concept and planar graphs, BL graphs and vertices of the and edge coloring and planar graphs and subgraphs and subsets, and these all the degrees and minimum degrees, observations, okay, vertices of the degrees and maximum degree of the vertices, timetable scheduling and the edge coloring and graph is discussed. Observed that is a edge chromatic number of one non-empty and finite graph is not less than the maximum degree of the vertices of the graph G. These are all the things we discussed. In our examination, you will ask that is a simple way of the questions. So concept-wise, you should be right. It is enough. Okay. Already questions and answers also will be there. You can try for that. Okay. This is an oral idea about it. Total concept of the today class. All are understood or not? Amma, in that, do you have any doubt?
No, sir.
No doubt, sir.
Okay, no. Anyway, okay, we will meet in the next class into the new topic.
Okay, sir. Thank you.
Okay.
Thank you, sir.
Okay, thank you, sir.